Mederic Gravelle, who is going to speak about a comparison of GPS-only and Galileo-only ambiguity fixed PPP solutions, insights from the Spot Genes Analysis Center.
Well, thank you, Paul, for the introduction. Hello, everyone. So my name is Mederic Gravelle. I'm working at Liens Laboratory at La Rochelle University in France. And I would like to show you today preliminary results on a study we have performed with my co-authors about the comparison of GPS-only and Galileo-only time series from Spot Genes Analysis Center. So this morning you heard a little bit about Spot Genes in Olivier Bock presentation, so I will explain a little bit in more details what is it. So Spot Genes is a cooperative project gathering people interested in GNSS processing for different applications. So each Spot Genes Analysis Center chooses the stations he wants to process. You can see here the actual Spot Genes network. And then is committed to use the same software, GENS, developed at CNES in Toulouse, in France. The same products from the CNES CLS IGS Analysis Center. And I encourage you to see the poster from Sylvain at the end of the afternoon. And the same strategy, same models, corrections, metadata. And this enables to an homogeneous dataset of GPS plus Galileo time series distributed on the Geodesy Plotter portal. And if you want to know more about Spot Genes, you can see, you can have a look to this data paper on the left that we have published last year. So the initial objective of the study was to evaluate the contribution of both constellations on our GPS plus Galileo products. So we processed GPS only and Galileo only time series for almost 800 stations. And the first comparison we did is to produce the periodograms to make sure that the contents in the time series are similar. And then we compare the dispersions in the time series. So in the GPS only time series and the Galileo only time series. So let's have a closer look to these dispersions. You can see on these scatter plots that sometimes for some stations, the dispersion of the Galileo time series is much higher than the GPS time series, like for this station in Japan. And in that case, it seemed to be due to a lack of Galileo observations. And what is interesting in that for many other Japanese stations with the same antenna model and the same receiver, we can observe the same behavior. So this is something we need to still investigate. For other stations, like this station in the Svalbard Island in Norway, this is the opposite. The dispersion of the GPS time series is higher than the Galileo time series. And in that case, it seems that GENS, the software, was unable to fix the GPS ambiguities, and we still need to understand why. But most of the time, the dispersions between GPS only and Galileo only time series look similar. Like you can see the example of this station in Argentina, Rio 2. But if we look carefully at the time series, we can see slight differences before and after this antenna model change in 2020. If we plot the time series of the difference between GPS and Galileo, we can see this offset that occurs at the antenna model change date. And this offset is about 8 millimeters. So the question of the impact of the calibration model raised, and we decided to process mean biases for each antenna and radome pairs per station. So this graph represents the compilation of all of these mean biases calculated. And you can see that these biases are at several millimeter level, and for some antenna and plus radome models, it can reach the centimeter level. The box plot in orange represents the antenna models, antenna plus radome models, for which the radome has not been calibrated. And all of these box plots are sorted by the number of individual antennas that have been used to establish the calibration table. But as you can see, there is no visible impact of this sorting. So if we sort the box plot differently, by the total calibration runs used to make the calibration model, we cannot see any clear impact, any clear correlation with the biases. And this is illustrated with the two following examples of antennas which have a significant bias. The first example is the antenna Leica AS11, and we can find this antenna for 6 stations in our analysis. You can see the numbers on the bottom of the plots. And these antennas are mostly installed in the GrafCan network in the Canary Islands in Spain. And you can see on this time series of differences that the bias can reach 1 centimeter on the vertical. So if we look at the antex file, you can see that the calibration tables for this antenna have been copied from another antenna without verification by calibration. So maybe this could explain the biases that we observed for this antenna. The second example is a Leica AR20 antenna with a random lane, which is actually highly represented in our analysis, since it concerns 73 stations. And if we look the antex file again, you can see that the calibration model has been provided with more than 60 different individual antennas and 138 calibration runs. But this does not avoid significant biases that we can observe for these stations, like, for example, this station in Spain located on the tie gauge of Cartagena. So the third conclusion is that from the scatter plots of the dispersions, we have seen some big differences between the GPS-only time series and the Galileo-only time series. And we still need to investigate these big differences to be sure that it does not come from our side, from our software. The second conclusion is that we have observed significant biases for several antennas up to 1 centimeter. But some of these biases have been calculated for only one antenna. So this means that this analysis needs to be strengthened, to be densified, sorry. And since this analysis is based on 800 stations, but according to the log files, we can see that up to 3,000 stations of the actual SPOGITS networks are recording Galileo with a calibrated antenna. So this is something we could complete this analysis in the near future. A second perspective would be to evaluate the impact of the receiver model on firmware. What we have done with the antenna plus radar models, we could also do it with different receiver and firmware versions. I don't know if you noticed on the Rio 2 time series of differences between Galileo and GPS, but something happened in 2021. Oops, sorry. In 2021, yeah, and we can see an offset that can reach several millimeters, and there is no antenna change at the date, at least according to the log file. So no antenna change, no receiver change, but it is only an update of the firmware version, of the receiver firmware version. So this is something we could also do in the future. Again, another perspective would be to evaluate the impact on the IGS products. As you can see on the graph on the right, over the 533 stations from the IGS, almost 14% are equipped with an antenna plus radome that appear to have a significant biases according to our study. So the question raised about the impact when new data from new constellation arrive in the IGS time series, or when we combine Galileo and no Galileo time series. And I would like to finish by telling you that all of these results are freely available to anyone who would like to compare probabilistic time series with other softwares or strategy. Thank you very much for your attention.